This is a review of the test of basic prerequisite take-home assignment. Trying to walk you through the way you can solve the different or answer the different questions here. So question 1, using a periodic table of element, calculate the molar weight of phosphate, orthophosphate PO4. So periodic table of element, you can find that lots of places on the web. Here's one pretty poor outfit, but it'll do. So what I need to do here is to know that what I want to find is the molar. I want to find the molar weight of the PO4. So the molar mass of PO4. Well, the molar mass of a chemical component that consists of phosphorus and oxygen, and here is interesting or important to notice there is one phosphorus atom and 4 oxygen atoms in this molecule PO4. So the molar weight of that is the molar weight of phosphorus plus 4 times the molar weight of oxygen. So I need to find the molecular weight, and I can do that in the periodic table of element. It's not so easy to see here, but phosphorus actually has a molar weight of 30.97, so roughly 31 gram per mole, oxygen 16. So here I've got 31 gram per mole plus 4 times 16 gram per mole. So I will end up with 95 gram per mole as the molar weight of PO4. Second question, wastewater containing 15 milligram of orthophosphate PO4, how many milligram of phosphorus is in 1 liter? So I have a concentration now of PO4, write this like that, 15 milligram PO4 per liter, this is given. So I know that this concentration is actually defined as the mass of phosphorus per volume of solution. So what I've got here is my mass of PO4 per my volume of solution. I know I've been given that I'm looking for 1 liter, so my volume of solution is 1 liter. So hence I can come from knowing up here that this is the mass of PO4 per volume of solution. So I simply have to isolate my mass of PO4. So the mass of PO4 here is equal to the volume of solution times the concentration. So 1 liter times 15 milligram PO4 per liter equaling 15 milligram of PO4. So now I found out how much PO4, but I really want to know how much phosphorus. So element P I've got. So I've got 15 milligram orthophosphate, but how much phosphorus do I have? So looking at this, I can find out that, well, I can see that for every 1 mole of PO4, I have the same number of moles of phosphorus, because for 1 unit of this 1 molecule of PO4, I have 1 phosphorus atom in it. So if I find out how many moles this is, I will know how many moles of phosphorus I've got. To find out how I come from mass to number of quantity of substance or number of moles, well, I use the relationship between moles, molar mass and quantity of substance, telling me that the molar mass of a substance equals the mass of the substance divided by the number of moles I've got, the quantity. So N denotes the number of moles. Here I know the mass of PO4, I know the molar mass of PO4, but I also know that I have a ratio of 1 to 1. So I could calculate, for instance, for PO4 that I would like to find out how many moles have I got. So N would then equal M divided by big M. small m mass divided by molar mass. So for phosphorus orthophosphate, I've got the mass divided by the molar mass, and in this case I have the mass equal 15, I have the unit here, 15 milligram, of course. So let me just write that a little nicer. So I have the mass, 15 milligram PO4. I have the molar mass of orthophosphate, calculated it up here, 95 milligram per millimole. The molar mass was 95 gram per mole, so now I have the milli in front of both mass and substance quantity, and hence I've got everything organized here, so it comes out in millimole. So I will have 0.16 millimole of PO4 in my 1 liter of solution. Knowing that NP equals NPO4, I have the same number of moles of the two, so that directly gives me that my number of moles of phosphorus in my 1 liter of solution is the same. And now I can go back and find the solution to my concentration question. So what is the concentration? What is the mass of first the mass of phosphorus in 1 liter of solution? Well, that's the molar mass of P times the quantity of P. So molar mass of phosphorus is 31 gram per mole. Now I've got 0.16 millimole. So I will get the result in milligram. Could say the molar mass would be equal to milligram per millimole, and hence I get a result here multiplying the two, which will be 4.9 milligram of phosphorus. So this is the amount of phosphorus that I have, how many milligram of phosphorus I've got in my 1 liter of 15 milligram per liter PO4 solution. Third question, how many millimoles is 10 milligram of phosphorus? So again, I've got the relationship N equal M over big M. In this situation, well, I'm looking for phosphorus, so I have my 10 milligram of P. The molar weight is 31 milligram per millimole, or gram per mole, same number. Now I just want my units to match here, milligram, so it gets to be millimole down here. So my results get out in millimole, and it's 0.32 millimole of phosphorus. That was how much phosphorus I have in 10 milligram in substance quantity. Question 4, ammonia oxidation. Well, we've got the equation there. If I write it up here, we've got NH4 plus 2O2. That will be oxidized into nitrate if we have the right conditions, the right bacteria available. And then we produce some hydrogen ions here, H+. So what I can see from my equation here is that for every 1 mole of NH4 plus that I've got, I have 1 mole of nitrogen. And my question here is to try to find out, well, how much oxygen do I need? So 1 mole of NH4 equals 1 mole nitrogen. The mass of nitrogen equivalent for 1 mole will be the molar mass of nitrogen times the substance quantity. So again, here I have to look up in my periodic table of the element, finding that nitrogen has a molar mass of 14 gram per mole, and I have 1 mole. So yeah, basically I get 14 grams of nitrogen as if I'm looking at a reaction with 1 mole, that equivalents 14 grams of nitrogen. So for 1 mole of ammonia and 1 mole of nitrogen here, I use 2 moles of oxygen. That's what my balanced equation will tell me. So I need to find out how much mass is 2 moles of oxygen. So the mass of oxygen will be equaling the molar mass times the number of moles. So the molar mass of molecular oxygen is 2 times the molar mass of atom oxygen. So that's 2 times 31 gram per mole. And now I know that the amount of the moles of oxygen I need was 2. So multiply with 2, so I get 2 times 16. The atomic weight, the molar weight of atomic oxygen is 16 and the molecular weight is 32. So 32 times 2, 64 gram of O2. So I have that for every gram of the ratio between mass of oxygen and mass of nitrogen is now to be determined. 14 gram of now that was the 64 gram of oxygen for every 14 gram of nitrogen that I transfer, oxidize. So I just have to calculate this ratio, and that gives me 4.57 grams of oxygen per gram of nitrogen. So this is the oxygen consumption associated with oxidation of ammonia. So for every 1 gram of nitrogen that I've got here, I need 4.57 grams of oxygen to oxidize it. Second question here, how does this influence the pH of the water? Well, as I can see from my reaction up here, I'm producing H plus at this process. When I'm oxidizing ammonia, H plus is produced. And since pH is defined as minus log to the concentration of H plus, the more H plus I get, taking the minus log to an increasing concentration gives me a lower pH. So the pH is lowered. You can also say that H plus is an acid and pH is a measurement of the acidity, and the low pH is the more acidic. So to some extent the pH will be lowered by this process. Okay. Now to growth rate of bacteria, depending on, well, there's a lot of stuff that could affect the growth rate of bacteria. First of all, always mention temperature. The warmer, the faster. That's the general solution, or the general answer there. We also have, of course, how much food is available. Also, we call this substrate, and we could talk about the type of substrate and the quantity as factors. So do they have, for instance, sugar, acetic acid, something very easy digestible, and is there enough of it? Could also be other types of substrate. It could be that we have bacteria that live from, for instance, the ammonia oxidizing bacteria, so then the substrate would be the ammonia. pH will very often be a factor affecting the growth rate. Any inhibitors could be toxic substances. They would lower the growth rate. And there could be a number of other factors affecting the growth, but those are just some of them. What about potential problems discharging nutrients into a lake? Well, nutrients are increasing the growth of algae. That could also be a thing increasing the growth of bacteria. But because any living organism needs nutrients for the growth, so when we have algae, they thrive from their substrate is CO2 and water, so they use sunlight as energy, but their substrate is CO2, and normally there's enough of that. N and P are typically the limiting factors for the growth of these organisms. So when N and P are limiting and we add more of that, well, then we'll have excessive algae growth. Algae might die, and algae consist of organic matter. So when the algae die and drop to the bottom, this organic matter will decompose, and in that process, when the microbes are decreasing or decomposing the organic matter, O2 will be consumed, and oxygen is very essential, and there's little of it in the water normally because it's not very soluble in water, so we will get O2 depletion. And depletion meaning that we will lack the O2, the O2 will disappear, and that is very bad for the environment. So that's essentially the process associated with increased nutrient discharging into the environment, into a lake. 7, what drives the transport of a chemical substance in the process of diffusion? Well, diffusion is a molecular process where we see that the substance move not because of convective transport, but because of small molecular movements where the substance constantly switch place with the neighboring molecule, and it's like if we drop a little bit of color in a glass of water, and if there's no movement in the water, well, the color will slowly get out in the clean part of the water. And what drives this process, this transport, is diffusion. And diffusion can be expressed by Fick's law, saying that the diffusive velocity equals a diffusion constant times a concentration gradient. So it's really the concentration gradient, the differences in concentration, that drives the transport, and the velocity is also depending on a substance-specific and solute-specific diffusion coefficient, but the concentration gradient is the driving force here. Right, what does the rate of diffusion depend on? Well, the rate depend on the diffusion. Well, it depends on the concentration gradient. It depends on the diffusion coefficient. That is substance specific. So big molecules like starch will diffuse slower than small molecules like sugar. It depends on what does it diffuse in. Is it air or water? So the solute diffusion in air is much faster than in water, and it also always depends on the temperature. The warmer, the faster the diffusion. Diffusion is a very important process in biological and in physical environments. So, well, that was actually, let's see, that was 8 here. We've got question 9 again, back to the thing about concentration. So now a little bit more complex. We have a solution with 10% aluminum chloride by weight, meaning that we have 100 grams of aluminum chloride per kilogram of solution. This solution has a density of 1.2 kilogram per liter. Well, we will have the aluminum chloride dissolve, and we want to know how much solution in grams do I need to have 100 gram of aluminum. So if I want 100 gram of aluminum, how much solution do I need? So what I'm really looking for here is the mass of solution that I need in order to have a mass of aluminum that equals 100 gram. So in order to get here, I need to go back a little bit and look at what I know. So I will look at the concentration given. So I call that C1. I have a 10% weight solution, meaning that this concentration here is equivalent to 0.10 kilogram of aluminum chloride per kilogram of solution. Because it's a weight thing. So, well, I'm looking for a concentration in a different unit. I want to know a concentration in how much mass of, not aluminum chloride, but aluminum per volume of solution. Because basically, not really. I'm looking for So I would like to know, for instance, how many milligram of aluminum per liter of solution do I have? To get there, I can use the relationship between the mass of solution. This basically is the mass of aluminum chloride per mass of solution. So my density gives me the relationship between mass and volume. So for my C1 solution, I have that a density, meaning the mass of solution per volume of solution equals 1.2 kilogram per liter. So C1 being, can it be expressed as was the mass per mass? Now I can substitute the mass up here by the density times the volume, so I can rewrite C1 as mass of aluminum chloride divided by volume of solution times my density, 1.2 kilogram. Now I would like to redo this, try to see if I can express this in relation to the amount of aluminum that I've got here. So I know that for every 1 mole of aluminum chloride, I have the same number of moles of aluminum. For every 1 mole of aluminum chloride, I have 1 mole of aluminum in it. So using my relationship between mass and molar mass, N equals M over big M, small m over big M. So I can rewrite this and say, well, the mass of aluminum chloride per molar mass of aluminum chloride is equal to the mass of aluminum over the molar mass of aluminum. And hence I can isolate my mass of aluminum and rewrite that. Say, well, that I have up here, the mass of aluminum chloride, I can express that as a mass of aluminum over a mass of molar mass of aluminum times the molar mass of aluminum chloride. So I could look at the ratio between the two. So the molar mass of aluminum chloride is the molar mass of aluminum plus 3 times the molar mass of chloride. That gives me 133.4 gram per mole. And the molar mass of aluminum is just 27. So I now have a relationship here between the mass of aluminum and the mass of aluminum chloride and the mass of aluminum. So I could substitute that and rewrite my C3. So using this, I can rewrite my C1, and I could write that instead of this, I will use this expression. So 133.4 over 27 times the mass of aluminum over the volume of the solution times the density, then what, 1.2 kilogram per liter. So back to my C2 that I was looking for. So now I can use my C2 here and substitute. Can see I've got if I can express C2 as a function of C1 because I have my C2 here. So what I could do is to say, well, C2 is equal to C1 times 1.2 kilo per liter divided by the 133.4 over 27. And that is equal to I could simply calculate all these numbers here and say that, well, that will be, since my C1 is known, I know that that's 0.1, so I could put that in here and I could calculate all the numbers, so that would be 0.1 kilogram aluminum chloride per kilogram solution, 1.2 kilogram per liter, and I get 0.0243, and the unit here is kilogram aluminum per liter of solution. So that is my C2 concentration. So that's another way to express the concentration of the same solution. Now I could then figure out what is the volume of solution I need if I want to have 100 grams of aluminum. So I would be looking for the volume of the solution would be the mass divided by the concentration. So I want 0.1 kilogram of aluminum, and I have a concentration of 0.0243 kilogram of aluminum per liter of solution. So I get my volume of solution out here in liters, 4.16 liters. So that's the volume. I was actually asking for how much in grams, so I could have made this a little easier. I could also say now if I have this volume, well, the mass of solution is the density of the solution times the volume. So it's 1.2 kilogram per liter times 4.16 liters. So that will be the 5 kilogram